rare disease diagnostic test. So the question is that we have a disease which has a diagnostic test. Diagnostic test is very good, and 90% of those with the disease are positive, but it is not, it has some false positive rate, and which is 5% only, which means that 5% of those without the disease are also positive. And the disease is fairly rare, it is only affecting 1% of the population. So obviously, as a clinician, you would want to know that if a person tests positive, what is the probability that he has the disease given a positive result. And the intuition would say that since 90% of the patients who positive with disease are positive, the chances are that the probability of disease given a positive result would be very high. But let's try to do it using Bayes principle. Bayes principle is that if you have two events A and B which are mutually exclusive and collectively exhaustive, then for another event D, the probability of B given D is probability of D given B times probability of B divided by probability of D. So this is nothing but the simple Bayes formula, and we do it using a figure like this. We have an A and a B, and this is the D which is overlapping there, which is the D. This is those without disease, and this is those with disease. So probability here, probability of D positive result given B is the probability of the test being positive in those with the disease, which we already know to be 0.9 or 90%, which we know from here. And what about probability of B? Probability of B is the unconditional probability of disease, which is 0.01. So only thing left for us to know is this, and this we have seen is probability of D, which is going to be probability of this, from this is D intersection B plus probability of D intersection A, which we know is going to be probability of D given B times probability of B plus probability of D given A times probability of A. Now what is probability of D given B is 0.9 times probability of B, it is 0.01. Probability of D given A is also there, which is probability of which is this number here. So this is 0.05, this is the false positive rate, times probability of A, which is very high, which is 0.99. So this all comes out to 0.009 plus 0.0495 this comes out to be 0.0585. Then putting this into the formula, because this goes here, which is going to be 0.09 or 0.009. So this is going to be probability of B disease given positive test is 0.009 divided by 0.0585. This comes out to be 0.154 or 15%. It is important to realize the critical impact of this is making in this. This is the probability of the disease. Since the disease is rare, its probability is 0.01%. If we just convert it to 0.1 or 10%, we do the math, it will come out to be 64%. So the two things that makes impact is the false positive rate, which is 5%, as well as the prevalence of the disease. So if the disease is very rare, even if the test you are doing is positive, has high degree of accuracy, the chances of a random person having the disease is going to be very low even if the test is positive. And that is why when ordering a test, we have to pre-select the people whom we are doing the test based on certain characteristics rather than randomly ordering test. Because if your population of interest is at very high risk, and sometimes based on clinical judgment you expect them to be at least 50%. Now if you change this to 0.5, let's change this to 0.5. If you change this to 0.5 here, now suddenly this will change from 0.9, will change to 0.45, and this will change to 0.0495 plus 0.45, which is going to be 0.4995, and of course this will also change to 0.45 divided by 0.4995. So 0.45 divided by 0.4995, it becomes 90%. So if it went up, only thing that has changed is that you have pre-selected the population which are at risk of having the disease, and suddenly the validity of the test result for patients who have the disease went up from 15% to 90%.